Measuring current is simple, right? You just take a multimeter, connect it to the two cables and read the value. If you want to do the same with a microcontroller like an Arduino or an ESP, things get a little bit more complicated. Let's dig into it to see how it works and which is the best sensor for our projects. Grüezi YouTubers, here is the guy with the Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. In this video we will look at the different methods to measure current, its advantages and disadvantages. We will see where we have to pay attention. We will look at some of the most popular boards. We will build an example with each board to see how they can be used. And in the end, you should know which module is best for your project and how to use it. As said before, measuring current is simple. Not as simple as voltage or resistance, because we have to think about changing one cable to a different connector. And then, usually we have the choice, like here, milliampere, microampere or 10 ampere. The first question is, why do we have to change the connector? And the second question, why do we need two different connectors? The first answer is, these multimeters can not really measure current. They only measure voltage. This is why they use Ohm's law for the current measurements. These meters have a resistor between the left and the right connector. And they measure the voltage across this resistor, use Ohm's law and show you the current. Simple. But why do we need two connectors? It is because of the burden voltage. If you want to know more, you can watch the video which is now appearing in the top right corner. It deals with measuring minimal currents like the deep sleep currents. In a nutshell, if we draw the full diagram of our current meter, including a power source like a battery and a load like an ESP8266, which consumes around 100 mA, we can do some calculations. If we want to make it simpler for our meter, we use a 1 ohm resistor. 100 mA leads to a voltage of 100 mV, which easily can be measured by the built-in meter. Unfortunately, this 100 mV is lost in this resistor. If the resistor would be bigger, the ESP would no more get enough voltage and crash. This is the reason for the second connector. Here a much smaller resistor is between the connectors, which leads to a lower burden voltage. We also have to keep the power dissipation in mind. If we used a 0.1 ohm resistor for the 10 ampere range, it would dissipate 10 watts. It would need quite a chunky resistor. Here I have a different multimeter without these additional connectors for current measurement, but with this clamp. This meter uses so-called Hall sensors to measure the magnetic fields. It measures the current contactless and without the burden voltage. It is essential that you only feed one wire through the clamp. If you feed both, it shows 0 because the forward and the reverse current are the same and cancel each out. How does it work? Current creates a magnetic field around the cable and this clamp picks it up. And if I wind the cable 2 times through the clamp, the current doubles. But also if I place a magnet near the clamp, it shows current from nothing. So pay attention with magnets. The current range is high, up to 600 ampere. It can measure current in both direction and also AC. But the accuracy is low as we see here. We now saw two ways of measuring current with multimeters. And here we have some corresponding sensors for our MCU projects. To begin with, we can measure currents on the low or on the high side. Now you could argue, why do we need an additional sensor? We can insert a resistor and measure the voltage across it with one of our analog inputs. Let's try it on the low side first. We insert the resistor and really we can measure a voltage. Now we could connect the analog input of the Arduino to the resistor. The first question is, on which side? The analog input of the MCU measures the voltage in relation to the ground. If we connect the input to this side, for sure we get 0 volts all the time. So we have to choose the other side. If I check with my multimeter, we see that this voltage is negative compared with the ground. And unfortunately, analog inputs are destroyed if they get too much negative voltage. Good, I checked before with my multimeter. Now you can say, add an inverting op-amp and you get a positive voltage. This is true, of course, but only if the op-amp has a plus and minus 5 volts supply. We would need an additional negative voltage. Not very convenient. So I would say we abandon this side and try the high side. This should work better. I insert the same resistor on the high side and measure precisely the same voltage. The same question here. Where to connect the input? We remember the analog input measures voltages in relation to the ground. So here it always measures VCC of the MCU. And here the voltage is higher than VCC, which again cannot be measured by the analog input. You can say, easy, add a voltage divider. Yes, I can add one, and it works. I can add an analog input to the voltage divider and subtract the two values without a sensor. Victory! We replaced a current sensor with two cheap resistors. Unfortunately, there is a drawback. The voltage across the resistor is the burden voltage and, as we saw before, it has to be small. Let's assume a 0.1 ohm resistor, 100 mA consumption and 5 volts. The analog input will measure 5.01 divided by 2 equals 2.505 volts because of the voltage divider. This results in 512 or 513 in the Arduino because of the 10-bit ADC. The other will measure the maximum value because it measures VCC, 1023. We multiply the first times 2 and subtract the second value. The difference is 1. If we would increase the load to 200 mA, we would measure 2.51 volts, which would result in 513 or 514. The difference are 2 digits for a doubling of the current. Very insensitive. Again, you can say, add an op-amp. Yes, here you're right. But let's look at the selection of the sensors I have here and see how they deal with those problems. The first category, the ones with the resistors, are Max 4080, an INA 169, an INA 219, and an INA 3321. The second category, the ones with Hall sensors, are the ACS 712, the ACS 758, and the WCS 1800. And a last one, which somehow fits in between, the LTC 4150 Coulomb counter. Most of the sensors of both categories have an analog output, and you need an analog input for measurement. The usual MCUs have built-in analog inputs, and you can use one of those if you are okay with the resolution. If not, you have to add an external ADC. If you create an analog circuit, you are fine without an ADC, of course. Two of the sensors come with a built-in ADC and an I2C interface. This is quite handy for MCU projects. Let's look at the sensors of the first category. The analog part of the sensors with resistors are very similar. They insert a small shunt resistor into the top side and contain more or less an op-amp. It is not a standard op-amp though. Let's look at the diagram of the INA 169. It can handle voltages up to 60 volts. And because it only measures the voltage difference across the smaller resistor, its common mode rejection and its offset voltage errors have to be very small. For the INA169, we can change two resistor values, RS and RL. Both influence the sensitivity of the chip. The board I have here has RS 0.1 ohms and RL 10K, which leads to a sensitivity of 1 volt per ampere. Let's check it out. I connect it to my R6006 power supply to create some current. The load is an IT8512A. We get very close to 1 volt for 1 ampere. At 4 ampere we only get 3.6 volts, so this configuration is suitable for up to around 3 ampere. One thing, however, is vital. You have to connect the ground of the load to the ground of your sensor and your MCU. Otherwise, you do not get correct values, and if you are out of luck, you destroy your sensor. If we increase the voltage, it does not matter. The reading stays the same. This op-amp is really quite precise. The minimum voltage depends on the current measured. It goes down to about 3 volts if you remain below 1 ampere. So it can be used for a single cell Li-ion MCU setup. Let's try the Max 4080. You only have one resistor to play with, R-Sense. Instead of changing RL, you get different versions of the chip. I have here the T version, which has a sensitivity of 20 volt per volt. I did not find a breakout board for this chip. This is why I have it on a breadboard. I use two 1 ohm resistors in parallel as R-Sense, which results in 0.5 ohms. 1 ampere should create 0.5 volts. Multiplied with the sensitivity of 20, it is 10 volts. You see, this is a very sensitive chip, and in this setup I only can measure up to around 400 mA. With a 0.1 ohm resistor I could measure around 2 ampere. Both chips are therefore suitable for small solar projects, for example. Otherwise, I have no preference. Let's have a look at the INA219. It has a so-called programmable gain amplifier, which is comparable with our op-amps from before. There are two differences. As the name says, its gain can be changed, and as we can see here, its input also can be switched. In addition to the former two chips, it has a built-in analog to digital converter and an I2C interface. This seems to be a neat chip. Let's look at how we can connect it to our project. As before, we add a resistor into the hot side, here called R-shunt, and connect Vin plus and Vin minus to this resistor. All as before. Fortunately, we get a ready-made library for the chip, and we can start it up. It not only shows the current, it also shows a voltage. This is because of this switch. If switched, the ADC measures the voltage of Vin minus to ground. Cool! With these values, we can also calculate power. Just to rant a little. The sketch mixes the bus voltage and the load voltage. The load voltage obviously have to be lower than the bus voltage. The breakout board also has a 0.1 ohm resistor, and the Adafruit sketch offers these three ranges. So it is perfect to measure the current produced by a solar panel or the current used from a battery, or both using two INA219. I also like the I2C interface because we can put the sensitive analog stuff close to the action and use longer digital wires to our MCUs if needed. This leads us to the INA3221 board. This chip has three sensors like the INA219 on one chip, which in principle would be perfect for a solar project where, as we saw before, need two INA219. Unfortunately, the designer of the board had a different scenario in mind and connected all Vin plus pins together. Like that, we only can use it in such a configuration. One battery with three loads. Not very intelligent. This one here seems to be better designed, but I do not have it right now. Before you order, look at the difference here. The better one has 2 ground pins and the other one 3 different pins. By the way, you also find boards with the INA226, which is very similar to the INA219. It has a slightly higher maximum voltage and an additional alert pin for overcurrent protection. All 5 sensors cannot measure reverse currents. Now we come to the sensors which use Hall elements. As we saw before, they have 3 significant advantages. The measuring circuit is electrically not connected to your supply cable, so they work on the low side as well as on the high side. They should not create a burden voltage because they just use the magnetic fields. But 2 of the 3 sensors in the test still have to be inserted inline. So presumably they also create a small burden voltage. They usually measure in both directions, and because of that, sometimes they also can be used to measure AC. If we look at their specs, we see that they are designed for high currents, which also means that they are not precise for small currents. And they can be influenced by magnets, as I showed with my clamp meter. Let's start with the smallest chip, the ACS712. It comes in 3 versions, 5, 20 and 30 ampere. It is only a tiny chip, and 30 amps seems to be quite a lot for this device, even if it uses 2 pins each for the connection to the load and the battery. I probably would stick to the 5 ampere version. Also, because of the sensitivity of the stronger ones is smaller. Theoretically, you can connect it to mains because the pins involved in the measuring are isolated from the pins connected to our MCU. However, I would not trust such a small chip and small distances. Anyway, I do not like too much working with mains. Let's hook it up. The first thing we see is that we get 2.5 volts out at 0 amperes, which is half of the 5 volt input voltage. If we increase the current, it adds around 0.18 millivolts per ampere and ends at 3.4 volts. The full swing is about 0.9 volts. If I reverse the direction, the voltage goes down and ends at around 1.6 volts. Also a 0.9 volt difference. So it seems to work. The same company produces a bigger brother, or is it a bigger sister? The ACS758. You get them for even higher currents up to 200 amperes. I have the plus minus 50 ampere type. It should create 40 milliampere per ampere. Let's check. Really, 2.5 volts with 0 ampere and 2.7 volts at 5 ampere. I really need a more potent power supply to test this beast. While I go and dig for a stronger power supply, you can hit the thumbs up button or subscribe if not done yet. And really, I found one which is good for 20 ampere. So we can continue. The result is as expected, around 3.3 volts at 20 ampere. So the sensor seems to work. And the distances are also much bigger. So if you want something for mains, this is probably the better choice. The last one, the WCS1800, looks a little like my clamp meter. It can be sleeved into a mains cable without cutting it. Its range is 35 ampere. If we hook it up to the 20 ampere, it shows 2.45 volts at 0 ampere and 3.7 volt at 20 ampere. So the sensitivity is around 60 millivolt per ampere. For a mains scenario, I would use this one. Also because I do not need to cut a wire, which is legally not allowed everywhere. The last board is a little special. They call the LTC4150 a Coulomb counter. It is a simple device which is attached to a battery. The chip counts the charges which go into and come out of the battery. It can be used to calculate the charging status of a cell in percentage. The chip simply generates an interrupt signal for each charge. According to another pin, the MCU gets the direction of the charge. If the battery is charged, it adds, and if the battery is discharged, it's subtracted from the actual percentage. So it is a combination of 2 current sensors and 1 voltage sensor. Summarized, today we tested 2 types of current sensors. The shunt type, which measures a voltage across a small resistor, and Hall sensors, which are electrically isolated from the power cable. The shunt types only work on the high side and create a burden voltage. They are electrically connected to the power source and do not work for mains. They also only can measure current in one direction. Their range is adjustable, but usually only up to a few amperes. Because of this small range, their precision is higher. You also get them with a built-in ADC and an I2C interface, an ideal combination for low-power microcontroller projects like solar power. These chips can also measure the voltage. You even get the INA3221 with 3 built-in channels. Perfect if you want to measure more than one current. Pay attention to which version you order. The Hall sensors are made for higher currents and therefore less sensitive and less precise. You get them for very high ampere ranges up to 200 ampere. They can be used on the high as well as on the low side, and they also can measure currents in both directions. Most of them still have to be electrically looped into the power line. I would not trust the smaller ones for mains applications. The WCS1800 worked with a completely isolated Hall sensor. What are my favorites? Definitely the INA219, or if I need more than one of them, the INA3221. For analog projects, I would probably use either the INA169 or the MAX 4080. For the ACS712s and the ACS758, I do not see a lot of needs because I have no projects with big motors. For mains projects, I probably would use the WCS1800s because of its strict separation. That was all for today. As always, you find all the relevant links in the description. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. Thank you. Bye.